Hello, my name is Mike Sharwood-Smith and I'm going to be talking about systematically aligning mind and brain using the Modular Cognition framework as a navigation tool. And I'm speaking to you from Edinburgh in Scotland. So, here's an overview of the talk. I shall be explaining cognition in mind and brain in very general terms to start with, then move on to the main point, which is the mapping problem, and finally giving you a whistle-stop tour through the Modular Cognition framework, which I'll come to in due course, and I'll explain a little more about it then. And finally some conclusions. So let's start. Explaining cognition in the mind and the brain. Okay, well, for me obviously there are two levels in which we can describe and explain what we're looking for. Cognition can be described in the mind, and theories about cognition can be developed in the mind, and the same goes for the brain. The brain, of course, is the domain of neuroscientists and the mind of psychologists. I'm going to ignore for the moment philosophers, artists, musicians and people with a particular ideology who may have their own special view of the mind. I'm going to keep strictly to a limited view of the mind for the purposes of this talk. And more specifically, I'm going to be looking for compatible accounts for a systematic comparison between the two. So one way of putting it is that the mind is a biological phenomenon, just as biological as the brain itself. They're intimately related, they are described and explained at a different level, but they belong to the same big biological story. So what's the mapping problem? The mapping problem was discussed by Popel in 2013, where he pointed out that maps can be made of the brain and neural structure. Maps can be made, as it were, of the mind, but the mapping problem is precisely how to draw one in alignment with another, so that, as it were, you can explain human behavior in terms of brain activity and brain systems and vice versa. Well, both mind and brain are very complex, but if we describe the mind, we are doing it at a more abstract level, and this allows a certain amount of simplification, relatively speaking. Whereas we are looking at neural networks in a complex brain, we need a very different approach. We are, after all, talking about different physical locations, we're talking about different physical pathways, and we're using different units to describe and explain what we see, and we're looking at different operating principles. Mapping the brain is not an easy matter by any long chalk, and the Human Connectome project makes that quite clear. This is a project that's started up in 2 universities in the United States, but is now a worldwide project with many institutions taking part. And if you go to the websites, you will find described the various aims, and one of them, the direct aim, is a comprehensive of neuronal connections within the human nervous system, and that image you see I took from one of those websites. The idea is to use the most sophisticated visualization techniques currently available, for example functional MRI amongst others, and the aim then is to capture the characteristics of the human species. Okay, we're talking about the modern human, and we're talking about a comprehensive picture of the organization of synapses and neurons, allowing for a very great deal of individual variation. No two brains, of course, are the same, even in twins. There is, however, and this interests me in particular, an ultimate aim, which takes you outside the domain of neuroscience, and it's to relate the two levels. as they say, using the wiring of the brain and connectivity strengths to relate brain circuits to human behavior. So this is a neuroscientific initiative to solving the mapping problem. My questions are the following. Once you have that connectome, what does it tell you about human behavior? This question has already been asked, by the way, because there are connectomes around. There's the connectome for the C. elegans, the roundworm, and it has actually been completed. And the question has been asked about, so what does it tell you about the C. elegans, in fact? So it's not a straightforward problem. And the second question is, how do you approach brain-mind mapping in the human species when there appears to be a lack of compatible, up-to-date accounts of the mind? It's as if the psychologists are not doing their job. That doesn't stop research, of course. A lot of very useful research can proceed according to what I call heuristic strategies. You can have a look to psychological research which zeroes in on particular mental phenomena. For example, dysfunctions, and that seems to be the main interest in neuropsychology, to look at certain diseases and disorders in the mind and find out what's going on in the brain and make appropriate associations. Or you can select familiar phenomena from everyday experience. So fear, for example, everyone has a good idea of what fear is. You don't have to necessarily go to experts to ask what fear is. You can use that as a basis for looking at fear in the brain. Better, of course, is to combine the two things, namely look at your everyday understanding of fear, but also looking at what is being done by psychologists who are also specializing in fear, and then proceed accordingly. And that, of course, is what Joseph Ledoux has been doing for most of his career. And, well, I have to say there is a fourth heuristic strategy, and that is simply to operate on general assumptions about how the mind works. And they may be unquestioned assumptions, or they may be based on some model which has been outdated or is no longer relevant. So a combination of heuristic strategies can get you quite a long way. However, it's not a systematic approach. That's what I'm looking for. So the modular cognition framework is not a theory of the whole mind exactly. You can get a model of the mind, a basic model of the mind out of it, but it's a framework for building such a model using the help from many different experts from different areas of cognitive science, including neuroscience, of course. And it's a sort of integration of research in various domains within contemporary cognitive science. There's a website, which I'll repeat at the end, where you can find many more details. So the idea would be, you've got a genome, you've got a connectome, how about having a psychome? I've heard it called other things, but I'm going to use the word psychome. What would a psychome be, apart from a matching contribution to the mapping problem from psychologists this time? Well, it would be, to use the phrase of the phraseology of the Connectome project, it would be a generalization that captures the characteristics of the human species. It would be a comprehensive picture of the cognitive organization of the mind. It would allow for a very great deal of individual variation. Like brains, minds are not the same. Every individual has a different one. And it will specify the general architecture of the mind, which will require elaboration. So the MCF, the Modular Cognition Framework, sees the mind as a network, a collaborative network with functionally specialized systems. That is a description that might also work very nicely for the brain as well. Let's compare vision in both the mind and the brain version of the MCF. The basic visual system in the brain, highly simplified, is still reasonably complicated. Here is a highly simplified picture of the visual system. not describing how it operates, but you've got the sort of basic way it's set up. You've got the optical pathways, you've got the cortex, various parts of the various component parts. You've only got the V1 cortex. The other areas above one are not displayed. And if you look now at the basic visual system in the mind, at this more abstract level, you have the following. You have a visual processing system and a store. So all of the systems are the same. They have the identical design, a processor and a store. And the processor incorporates all the unique principles of human visual cognition. In other words, human as opposed to other species, and visual as opposed to other types of system elsewhere in the mind and brain. And there is a store where representations of the visual world are stored, amended, added to over the lifetime. Again, take the spatial system. We have a spatial system in the brain, we have a spatial system in the mind. Here it's nicely wrapped up in a basic design of processor and store, and indeed the processor incorporates the special principles of human spatial vision. And likewise for meaning, you might call this a semantic processor, but it certainly incorporates more than language. The conceptual processor and the conceptual store do the same job, but they're following principles of conceptual cognition. All these unique biological principles represent our, as it were, biological starter set, our biological inheritance, what we inherit as humans. So here's a very rapid taster of the overall architecture that I showed very briefly earlier on. The MCF system we can look at as composed of two rings of specialist systems, two rings. Here's the outer ring, which you could call the Perceptual Gateway. It creates representations from different types of sensory stimuli. Okay, you've got the olfactory system, the gustatory system, the olfactory system, the visual system, which we just talked about, the auditory system, and the somatosensory system. So they are, as it were, our portal. It's the closest part of cognition to the outside environmental reality. We have an inner ring. We got an affective system, which takes care of value and the basic emotions. We've got the motor system. We have two linguistic systems. We have the meaning system that I just described, the conceptual system, and we got the spatial system, which I also mentioned. And these are important, and representations in all of these areas need to be associated with something else to solve any particular task that we come up with, millisecond by millisecond. So there's the complete network again, without the operating principles, but I haven't even put in any pathways, so let's do that very briefly in the minutes we got left. These pathways in the mind allow you to connect and associate different representations that are put together in different ways, but nevertheless you can form an association between them, and once they're associated, if one gets co-activated, the other one does. And activation is a matter of degree. Here's the example of Latin. I don't know why I said that. Of the affective system. Affect, as you say, incorporates value. So here it is in its position in the ring, and here it is with all the other systems, and it has connections that radiate throughout the network. And if, for example, you have a value, highly positive value, connected with a particular image, a visual representation, then that visual representation will have an immediate association and therefore will be co-activated with the value. So immediately this particular visual representation is activated to a greater or lesser degree. It will its value will determine exactly how much it has been activated. Right. Most representations can be connected via the direct links here between the effectors. So these are, as it were, pathways for establishing associations. There's no passage through the pathways, simply an associative networks are formed which then co-activate to a greater or lesser degree. The important thing about effective representations is that they have a very great influence on the degree of activation of particular representations with which they are associated. Okay, summing up, after this rapid whip through the modular cognition framework architecture, we can say that despite the use of shared or similar basic concepts, mapping the mind requires a different, separate approach. You have, after all, not physical locations, you have abstract locations, you have abstract pathways, you talk in terms of different units, and certainly different operating principles. Some of the operating principles work only within a particular system, but there are general operating principles that work across the whole mind. So the conclusions are that the biological approaches to the mind are required for systematically relating brain and mind phenomena, so not purely heuristically, but systematically, and the MCF aims to provide, amongst other things, a navigation tool to assist such mapping between neural systems and the mind. And that really is where I stop. So thank you very much for listening to me. Visit the website if you want more details. And that completes my 17 minutes. Thank you very much.